In segment 1.1, we're going to talk about cryptographic hash functions. We'll talk about what they are and what their properties are. And then later we'll move on and talk about what their applications are. So a cryptographic hash function is a mathematical function, and it has three attributes that we need to start with. First of all, a hash function can take any string as input, absolutely any string of any size. It produces a fixed size output. We'll use 256 bits in this series of lectures because that's what Bitcoin does. And it has to be efficiently computable, meaning given a string, in a reasonable length of time, you can figure out what the output is. So that's a hash function, but we're going to need hash functions that are cryptographically secure. The cryptographic properties of hash functions are a complicated topic in general, but we're going to focus here on three particular properties, and I'll explain in a minute what those are. In particular, that the function is collision-free, that it has a hiding property, and that it's puzzle-friendly. And for each of these, I'll talk about what the property is, what it means, and then I'll talk about why it's useful to have a function that has that property. So first, collision-free. So the first property that we need from a cryptographic hash function is that it's collision-free. And what that means is that it's impossible, nobody can find values x and y such that x and y are different, and yet the hash of x is equal to the hash of y. And so if we look at the operation of the function as depicted by one of these red arrows, here's x and h of x, and here's y and h of y, then nobody can find a situation like this, that you have an x and y that are separate, and yet when you hash them, they hash to the same value. Now, one thing to notice is that I said nobody can find. I didn't say that there is no collision. Because if you think about it, there has to be a collision. Collisions do exist, and to understand why that is, we can use this diagram. Over here on the left, I'm depicting all of the possible inputs to this function, which can be a string of any size. And over here, I have all of the possible outputs, which has to be a string of 256 bits in size. So the right-hand side here, the outputs, there are only 2 to the 256 possibilities. Over here, there are more possibilities. And so if you think that every point over here on the left is going to be mapped by an arrow to some point on the right, you can see that as you go from all the points over here on the left into the right, it has to get crowded, and in fact, that there have to be multiple values over here on the left that map to the same output over here. In fact, in general, there will be a very large number of possible inputs that map to any particular output. So collisions do exist. I said before, nobody can find a collision, and that's the key question. We know collisions exist. The question is, are there any collisions that are findable by regular people using regular computers? Okay. Now, to make things even worse, I said that it has to be impossible to find a collision. Let me tell you how to find a collision, because there's a method that's guaranteed to work. And the method works like this, that we're going to pick 2 to the 130 randomly chosen inputs over on the left cloud of that previous diagram. And if we pick those 2 to the 130 randomly chosen inputs, it turns out there's a 99.8% chance that at least 2 of them are going to collide. And so this is a very simple method for finding a collision. It works no matter what the hash function is, but of course the problem is that this takes a very, very long time to do. You have to compute the hash function 2 to the 130 times, and that's of course an astronomical number. This method works no matter which hash function we're using. There's still a 99.8% probability that this works, and if it doesn't work, just try it again, and it'll probably work the next time. But this doesn't really matter, and the reason it doesn't really matter is that this procedure takes 2 to the 130 steps in order to get to that high probability. So we can say something like this. We can say that if every computer ever made by humanity was computing since the beginning of the entire universe up to now, the odds that they would have found a collision is still infinitesimally small. So small that it's way less than the odds that the Earth will be destroyed by a giant meteor in the next 2 seconds, which didn't happen. Okay, so we know how to find a collision, but this method takes too long to matter. The question is there some other method that could be used on a particular hash function in order to find a collision? And that's the question that is harder to answer. Is there a faster way to find collisions? Well, for some possible values of hash functions, of course there are. For example, if our hash function were to simply take the input modulo 2 to the 256, that is, it just selected the last 256 bits of the input, then we would know an easy way to find a collision. One collision would be the values 3 and 3 plus 2 to the 256. So for some possible values of the hash function, it's very easy to find a collision. For others, we don't know. Now, one thing I need to note is that there's no hash function in existence which has been proven to be collision-free. There are just some that people have tried really, really hard to find collisions and haven't succeeded. And so we choose to believe that those are collision-free. Okay. Now, what good does collision freedom do us? If we can assume that we have a hash function that is collision-free, then we can use that hash function as a message digest. And what I mean by that is the following, that if we know that x and y have the same hash, then it's safe to assume that x and y are the same. Because if someone knew an x and y that were different that had the same hash, of course that would be a collision. Since there's not a collision that we know of, then knowing the hashes are the same, we can assume that the values are the same. And this lets us use the hash as a kind of message digest. Suppose, for example, that we had a file, a really big file, and we wanted to be able to recognize later whether another file was the same as the file we saw the first time. Right? So one way to do that would be to save the whole big file, and then when we saw another file later, just compare them. But because we have hashes that we believe are collision-free, it's more efficient to just remember the hash of the original file. Then if someone shows us a new file and claims that it's the same, we can compute the hash of that new file and compare the hashes. If the hashes are the same, then we conclude that the files must have been the same. And that gives us a very efficient way to remember things we've seen before and recognize them again. And of course, this is useful because the hash is small. It's only 256 bits, while the original file might be really big. So hash is useful as a message digest, and we'll see later on in this lecture and in subsequent lectures why it's useful to use hashes as message digests. So the second property that we want from our hash function is that it's hiding. And the property that we want is something like this, that if we're given the output of the hash function, that there's no feasible way to figure out what the input x was. The problem is that this property doesn't exactly hold. And to understand why that's the case, let's look at this example. So here, what we're going to do is an experiment where we flip a coin, and if the result of the coin flip was heads, we're going to return the hash of the string heads, and if the result was tails, we're going to return the hash of the string tails. And now we're going to ask someone who didn't see the coin flip but only saw this hash output to figure out what the string was that was hashed. That, of course, is going to be easy. It's easy in this scenario to find what the input string was. It's easy to find x. You simply compute the hash of the string heads and the hash of the string tails, and you see which one you got. And so in just a couple of steps, you can figure out what x was. So the reason this example failed, that is the reason why an adversary was able to guess what the string was that there were only a couple of possible values of x. And so if we're going to have a hiding property like this, it needs to be the case that there's no value of x which is particularly likely. That is, x has to be chosen from a set that's in some sense very spread out, so that this method for the adversary of just trying all the possible values of x, or just trying a few values of x that are especially likely, is not going to work. So the hiding property that we are going to need to set up is a little bit more complicated. And the way we're going to fix this problem with the common value x, like heads and tails, is we're going to take the x and we're going to put next to it, we're going to concatenate with it a value r, which is chosen from a distribution that's really spread out. And so this h of r concatenated with x, that means take all the bits of r and put after them all the bits of x. And so what we're going to say is, given the hash of r together with x, that it's infeasible to find x, and that this will be true in the formally stated property that if r is a random value chosen from a distribution that has high min entropy, then given the hash of r concatenated with x, it's infeasible to find x. And what does high min entropy mean? Well, it captures this intuitive idea that r is chosen from a distribution that's really spread out. And what that means specifically is that there's no particular value that r could have had that would occur with more than a negligible probability. So for example, if r is chosen uniformly from among all of the strings that are 256 bits long, then any particular string was chosen with probability 1 in 2 to the 256, which is truly a negligible value. So as long as r was chosen that way, then the hash of r concatenated with x is going to hide x. And that's the hiding property that the hash function will be deemed to have. Okay, now let's look at an application of that hiding property. And in particular, what we want to do is something called a commitment. And this is kind of the digital analogy of taking a value, a number, and sealing it in an envelope and putting that envelope out on the table where everyone can see it. Now, when you do that, you've committed to what's in the envelope, but you haven't opened it. It's secret from everyone else. Later, you can open the envelope and get out the value, but it's sealed. So commit to a value and reveal it later. We want to do that in a digital sense. So to be more specific about what is the API that we're going to provide here, the commitment API looks like this, that there are two things you can do. First, you can commit to a message, and that's going to return two values, a commitment and a key. Think of the commitment as the envelope that you're going to put on the table, and the key as a secret key for unlocking the envelope. Then later, you allow someone else to verify, given a commitment and given a key which you've told them in the meantime, and the message, they can verify that that commitment, key, and message really do go together, and this will return true or false. Okay, now to seal MSG in an envelope, what we do is we commit to the message, and that returns a commitment and a key, and then we publish the commitment. That's putting the envelope on the table. Now later, to open the envelope, what we're going to do is publish the key and the message that we committed to, and then anybody can use this verify call with the commitment that we published previously, the key and message that we just announced, to check the validity of our opening the envelope. Okay. And the property, of course, we want from this is that it behaves like sealing an envelope. And in particular, the two security properties are these. First, given COM, the commitment, the envelope on the table, that someone just looking at the envelope can't figure out what the message is. The second property is that it's binding, that when you commit to what's in the envelope, you can't change your mind later. That is, it's infeasible to find two different messages such that you can commit to one message and then later claim that you committed to another, and the whole thing will verify. Okay, so how do we know that these two properties hold? Well, first we need to talk about how we're going to actually implement commitments. And the way we're going to implement commitments is like this. That in order to commit to a value message, we're going to generate a random 256-bit value and call it the key. And then we're going to, as the commitment, return the hash of the key concatenated together with the message. And as the key value, we're going to return h of this key. And then later, to verify, someone is going to compute this same hash of the key they were given, concatenated with the message, and they're going to check whether that's equal to the commitment that they saw. Okay, so this is a way of using hash functions both in the commitment and in the verification. So now the security properties, if we go down to the security properties that were at the bottom of the previous slide, and we just plug in the definitions of how we're going to implement this here, that is, this used to say COM, given COM, infeasible defined message, we just plug in what COM is. COM is the hash of key concatenated with message. And similarly down here, this is what happens when we take what was written there before and plug in the definition of verify in COM. Okay, so now what these properties become, the first one is given h of key concatenated with message, it's infeasible to find message. Well, it turns out that that's exactly the hiding property that we talked about before. Key was chosen as a random 256-bit value, and therefore the hiding property says that if we take the message and we put before it something that was chosen from a very spread out distribution, like I said, a random 256-bit value, then it's infeasible to find the message. So this is exactly the hiding property. And this one down here turns out to be exactly the collision-free property. So that if someone can find two messages which have the same hash like this, well, then they have an input value here and an input value there that are different, and yet those have the same hash. And so because of the two security properties we've talked about for hashes so far, this commitment scheme will work in the sense that it will have the necessary security properties. Okay, so that's the second security property of hashes, that they're hiding, and the application of that is commitments. The third security property we're going to need is that they're puzzle-friendly. And this is, again, a little bit more complicated, but let me just go through it a bit by bit. That for any possible output value y that you might want from the hash function, we're going to use y as an output value of the hash later, that if k is chosen from a distribution that has high min entropy, that is, k is chosen randomly from some set that's super spread out, then there's no way to find an x such that the hash of k and x is equal to y. So what this means is basically that if someone wants to target the hash function, if they want it to come out to some particular output value y, that if there's part of the input that is chosen in a suitably randomized way that it's very difficult to find another value that hits exactly that target. So the application we're going to use of this is we're going to build a search puzzle. And what that means is we're going to build a mathematical problem which requires searching a very large space in order to find the solution, and where there's no shortcuts, a way to find a good solution other than searching that large space. That's a search puzzle. To be more specific, the idea is that if we're given a puzzle ID, which is chosen from some high min entropy distribution, that is some very spread out probability distribution, and we're given a target set Y, which someone wants to make the hash function fall into, then we want to try to find a solution X, so that if we hash the puzzle ID together with the solution X, we get a result that's in the set Y. So the idea is Y is a target range or set of hash results that we want. ID specifies a particular puzzle, and X is a solution to the puzzle. And the puzzle-friendly property here implies that there's no solving strategy for this puzzle, which is much better than just trying random values of X. And so if we want to pose a puzzle that's difficult to solve, that we can do it this way, as long as we can generate puzzle IDs in a suitably random way. And we're going to use that later when we talk about Bitcoin mining. That's the sort of computational puzzle we're going to use. Okay, so we've talked about 3 properties of hash functions and 1 application of each of those. Now let me talk just very briefly about the particular hash function we're going to use. There are lots of hash functions in existence, but this is the one Bitcoin uses, and it's a pretty good one to use. It's called SHA-256, or SHA-256, and it works like this. Basically, it takes the message that you're hashing, and it breaks it up into blocks that are 512 bits in size. The message isn't going to be, in general, necessarily exactly a multiple of the block size, so we're going to add some padding at the end. And the padding is going to consist of, at the end of the padding, a 64-bit length field, which is the length of the message in bits. And then before that, it's going to consist of a 1-bit, followed by some number of 0 bits. And you choose the number of 0 bits so that this comes out exactly to the end of a block. So once you've padded the message so that its length is exactly a multiple of the 512-bit block size, you then chop it up into blocks, and you then execute this computation. You start with a 256-bit value called the IV. That's just a number that you look up in a standards document. And then you take the IV and the first block of the message. You take those 768 total bits, and you run them through this special function C, the compression function, and out comes 256 bits. You now take that with the next 512 bits of the message, run it through C again, and you keep going. Each iteration of C crunches in another 512-bit block of the message and mixes it in sort of logically to the result. And when you get to the very end, you have consumed all of the blocks of the message plus the padding. The result is the hash. That's a 256-bit value. And it's easy to show that if this function C, this compression function, is collision-free, then this entire hash function will also be collision-free. The other properties are a little bit more complicated, so I won't talk about them here. Okay, so we've talked about hash functions. We've talked about what hash functions do. We've talked about 3 properties of hash functions and applications of those properties, and the specific hash function that we use in Bitcoin. In the next lecture segment, we'll talk about ways of using hash functions to build more complicated data structures that are used in distributed systems like Bitcoin.